talking about orbital angular momentum. So remember, to refresh your memory, we were talking about micromanipulation or trapping or whatever you want to call it, using differently shaped lights, especially in terms of what sort of momentum they carry. So we were talking yesterday about linear momentum and angular momentum. We started to talk about angular momentum, and we talked about spin. And today I will want to talk about orbital angular momentum, and then go back and forth between spin, orbital, and linearly polarized light as well. Okay, so just to impress you, I hope this film plays. I have to do what Sean did and tell you where I'm from. So this is Google Maps. Zooming in onto our campus. Here's our campus, here's our wonderful building, and here's my lab. One of my labs where we are building, for example, dual optical tweezers. So typical laser, typical bits and pieces, so fiber laser and few bits and pieces to build dual tweezers. And off we go to the microscope, high molecular aperture, objective from below, light comes through, and then is reflected, and then goes to detector that I was showing you before. And we can manipulate particles in micron-size scale, and we can build double traps. So here's, I don't know whether it's visible, but there's a particle wiggling in the trap, and I was showing you the landscapes of the two traps before. And this is how it looks on the detector. And then you can do it with a very fast camera as well, so we've done that as well. So this is just a little
Who did that? How did you do that? The movie.
That was done, there is some special program that my postdoc was using, and it's all put together. It's a little bit too fast, I thought, but you cannot slow it down very much, I think. Okay, so if you take orbital angular momentum beams, which are Gauss-Laguerre beams of light, you can start playing with them. Unfortunately, we cannot see the beam because it's infrared, obviously, but there's the beam. And it's Gauss-Laguerre 0.3, which means it carries 3 h-bar angular momentum per photon. And you see that you can trap particles, and as soon as we have a shape of some sort, then it starts rotating. And of course, here the particles, it's quite strong trap, so the particles are drawn into the trap from quite far away, and they can then agglomerate in the trap in 2 dimensions. And you can go on like that. You can basically, if you make the trap even stronger, then you have this flower growing onto the sides. Again, not that you can use it for much, but it's called self-assembly, I suppose. Okay, and so what we can do now is to ask, if I have this rotation like that, for example, here I have Gauss-Laguerre 0.2, so it's again a beam with a vortex in the middle, and it has a 2 h-bar angular momentum per photon. And I have this dumbbell, and I put it into because it's an elongated particle, I can put it into this orbital angular momentum carrying beam, and it will rotate. But the question that we ask always is, can we do measurement of the orbital angular momentum? Can we decide how much orbital angular momentum has been transferred? So again, I can show you that we can now vary the geometry of the beams, vary the geometry of the trapped object, and then try to assess how much orbital angular momentum we transfer. So okay, so here is again LG02, so we marry it with an object which will best spin in this sort of beam, and then we go further and we go to LG04, okay, and so this is beam carrying 4 h-bar angular momentum, and you can see we have 4 particles. And what happens then is that the light which is emitted through the particle, exit beam will be changed. And if we know the incoming beam onto the particle, which is LG04, and if we can assess how this beam has changed and what the changes are quantitatively, we can then assess, calculate how much orbital angular momentum has been transferred. And so here, basically what we have, if I have these 4 particles, then the total change of L will be 0 in the beam. So I should have back my beam that I put in. Okay, so if I now take, I will come back to that determination of orbital angular momentum, but if I have non-axis metric object, then one big advantage of it, if you want to use it for any transfer of orbital angular momentum, is that you do not need any birefringence. Okay, so that's one thing. And then we also have high angular momentum flux, which is available to us in that situation. And it is better than birefringence, which I will show you a little bit later. And I can also create the objects, non-axis symmetric objects that I want to rotate in the beam using two-photon photopolymerization process. This is pretty easy to do. We can achieve very high optical quality, and we can have sub-wavelength resolution for this purpose. So here are, for example, some sort of cogs that can be produced using this method of two-photon photopolymerization process. So normally, when we are talking about MEMS devices, so this is from the Sandia webpage, you can see that there can be very, very intricate structures. However, scale-wise, they are still quite big. So this is a bar of 10 micron, so these machines are of orders of hundreds of microns in size. Now, we can now develop methods for production, and these are driven by electricity, obviously. Now, we can produce machines like that, or similar to those, using optical fabrication. And the scale here is about 9 microns across. And you can have quite sophisticated bits and pieces in it, details, and quite high resolution. So, as I said, what we do, we want to produce these elements for rotation. We can use Gaussian beams as well. We can measure angular momentum, and we can optimize by choosing the shapes of our objects, depending on what beams we are using, with which beams we are using, and what sort of transfer of momentum we want to have. We can optimize this transfer of angular momentum by optimizing the shapes of the particles. So we can calculate them and calculate the shapes and do the calculations using FDBT and see what sort of shape of the particle the object would be best for maximum transfer. Okay, so how does the process look like? So we have two photon process here involved. So normally if you have a normal excitation, one photon excitation, so here we have under the microscope, we have a volume here with a dye, and we send the light through it, and we see fluorescence through that, through the entire thickness, through the entire thickness of this sample. However, if I go to two photon processes, what you can see is the same sort of objective here, and you can see the little spot here of light, which is the same, the sample is filled with the same sort of dye in both cases. But obviously here, the light, the two photon process will occur where the intensity of the light is the strongest, and therefore it will be in the focal spot. Now, if you can imagine that I either manipulate the beam or I manipulate the stage of the microscope, I can move this spot to different positions. And if I have some special resin in this sample chamber, I can start playing chemistry using this sort of process. And so this is what's done in two-photon photopolymerization. This is work done a long time ago by Kawata's group. This ball is about 15 microns in size, or 10 microns in size. And you can see that the details with which you can produce structure like that are quite amazing. So what you do is that you fill your sample chamber with resin, and it's a resin which, when exposed to ultraviolet light, it hardens. So the refractive index of the resin changes when it is exposed to ultraviolet light. And so what we do, we use two photons of around 780 or 800 nanometers. So all up, we are now playing, if it's two photons, we are playing with the light which will photopolymerize the resin at 400 nanometers. And so the resin will get hard in a given spot. And then if I have cleverly programmed my stage of the microscope, I can move that spot around and photopolymerize whatever object I want. Okay? So this is the SEM picture of the microball that he produced. So the typical setup is very simple actually. In order to get these very high intensities of light, we use femtosecond laser. So I have a femtosecond laser here going onto my microscope slide, where I have my resin, and then I can also combine it. So I produce my structures, but what I want to do later is to take those structures and start rotating them, trapping them and rotating them. So I combine the setup with optical tweezers setup. So here is normal optical tweezers setup. Again, using laser, whatever hologram, if we want to have Gauss-Laguerre beams of light, I'll have hologram here or SLM, and then the light shaped in a particular way goes to my structure. I somehow build a setup in such a way that I can free the structures from the substrate, and I can trap them, and then I can look at them using my, you see here is the setup that I was showing you before, where we can measure the change in polarization or whatever we want to measure, or any detectors we want to put in order to analyze how much auto or spin or whatever momentum we have transferred to the structure. What is not shown here is how we actually kick off the structures that we build on this stage, and we basically have a little setup which mechanically can free the structures from the substrate. So this is how the structures are produced. So we're scanning the sample of a predetermined 3D shape, and we can produce whatever structures we want. So here is highly focused laser light, and I can build a cross or ball or whatever I want to build. Okay, and I'll show you a few examples of that. So you cannot see anything here. So this is our advertisement, so I will skip that, because if you come from Australia, you have to build things. And you see the little kangaroo, so this is photopolymerized kangaroo. The dream is to have a skipping kangaroo if we're from that side of the world, which we also had. So we had his leg on a hinge here, and he could jump, but he's still two-dimensional rather than three-dimensional. We made three-dimensional kangaroo, but it looked like a rat, so nobody did it. Okay, so this is the process. So for example, I want to create offset cross, non-axis symmetric object, for example. So I expose the resin when the pixel is set to black, okay, and then I build a bitmap, and eventually I have my cross. I can make it in 3 dimensions, or have a stalk coming in both dimensions to make it stand up in the beam. I don't know whether we discussed it or not, but if we have elongated particle, elongated object in a Gaussian beam, normally the particle will always, if it's elongated particle, it will always try to stand up in the beam. So to prevent that, what we can do is we can create the elongation along the axis coming out of the board here, and so this cross will be always, the sort of pieces of the cross will be always in the beam. We will force the dimensions of it. Okay, so fabrication process, I hope you can see that. So this is fabrication process. It's very, very slow, or comparatively slow, and you can see this is obviously optical microscope, because it's in the optical microscope we do it. You can see a structure being produced. So here is the start, we build a stalk, and then eventually the offset cross is being built. And one by one we can build it. Now, obviously there are methods. When you use holographic tweezers, there are methods which will enable us to build many such structures at any given time, if we are clever enough with that. So this is what we build. So this is scanning electron micrograph of the offset cross, and this is what we plan to build. So it looks pretty good, and we can rotate it. So we now put it into linearly polarized light or circularly polarized light, it doesn't matter, and it offset cross, because it's not axis symmetric, it will spin. And it's can you see this? It's 3-dimensionally trapped, so there is a little bit of resin on the microscope slide, and we can sort of drive it on top of it. And very soon you can see that we change the direction there, and then we can spin it very, very fast. Spinning rates of this offset crosses can be in hundreds of hertz. Okay, and this is just the evidence that it's three-dimensionally trapped. And you don't need a lot of power here. We are using 150 milliwatts before the objective. Objective is normally something like 50% efficiency, so at the sample we have 175 milliwatts. And we can get 10 hertz per 100 milliwatts of laser power. So if you have a lot of laser power, those resins are not very absorptive, so you can use a lot of laser power without burning them. But obviously, if you go too high up, you will burn them.
That was Gaussian beam illumination?
Yeah, that was Gaussian beam. Because the cross is non-axisymmetric, then it has a shape birefringence, so you can rotate it using that. So what's the resolution of two-photon photopolymerization process? This is due to the non-linearity of the process, and we can get beyond diffraction limitation. It's given by the smallest polymerized volume, which is called voxel, and here is our voxel. It's really not very visible, but anyway. So we are using immersion oil objective, which is numerical aperture 1.3, and the lateral resolution is about 100 nanometers. And the axial resolution is a little bit worse, it's 200 nanometers. There are groups where people are working on getting much better resolution than what we have in two-photon polymerization process. They are down to about 10 nanometers, 10, 20 nanometers. So you can do tricks, chemistry tricks, and use very special resins and so on, and so you can improve it on that resolution. For our purposes, it's not very important, and also we can overlap voxels so that the structures can look very, very nice. So if we look at our offset cross, we can make calculations using fluid dynamics package, and we know the size of the photopolymerized offset cross from our microscope and other measurements, and so we can input all those parameters and we can calculate what's happening, what the flow looks like around the cross. So this is we now switch gears and we go to symmetric cross. So this is axisymmetric object. Now I take this axisymmetric object and I put it to Gauss-Linear beam of light. And so now I am trying to transfer orbital angular momentum to that. And I'm hoping that I have film here. Okay. No? Will it play? Okay. So this is a symmetric cross in LG02 beam. And there's a little bit of structure again on the microscope slide. So this is just to show you that firstly we can rotate it, and secondly it's trapped three-dimensionally. So the big advantage is that it's free from the slide, and you can see that we can hold it and it tweezes quite easily. It's not spinning very fast, but again, if I increase the laser power, I can spin it much faster than that. And of course, this cross is produced using the same processes I was showing you before. We can do the same sort of calculations for using fluid dynamics to see how the fluid looks around those crosses. Again, inputting parameters from the geometries that we know from other classes. Okay, so again, two-photon photopolymerization, to remind you, we can do fancier things than that. So, at the moment, in order to produce Gauss-Linear beams of light, I either used SLM or I used holographic plate on which I produced a pattern which, when illuminated with Gaussian beam, would give me Gauss-Linear beam of light of the sort I wanted. However, it would be probably slightly easier for alignment purposes if I could have this mask put onto the microscope slide directly, and then just have illumination always being Gaussian beam, and then shine it through a mask which would be a micromask, which will then produce on the microscope slide, at the object, will produce a Gauss-Laguerre beam of light. So this is what we do here. So again, we have our photopolymerization laser here, 10-second laser, 3D piezo stage. And now what I want to build is I want to build a hologram which, when illuminated with the Gaussian beam, will give me LG02 or 04 or 03 structure. So basically, I first do photopolymerization. I keep that photopolymerized structure on the microscope cover slip, and we see what we are doing with that. And then I put my normal tweezing laser in. This is the structure I built. So this is structure which will give me Gauss-Laguerre 04 beam. And this is the map which we are building. And then, if I can combine it with my symmetric cross, which I also build on the microscope slide, but after building it, I free it from the microscope slide. I leave that one on it, and this one is in the solution. And then I combine the two. Then I can have two-photon photopolymerization of micro-optical diffractive elements. So this is the diffractive element. It doesn't look as nice as my plane, but it's pretty good. And this is the optical image of it. Okay. And so, is it here? Okay. And so what we are after, as I said, I take TEM00 linearly polarized light, I put it through the phase hologram, depending on how the phase hologram looks like. So this is the photopolymerized phase hologram, which is probably something like 5 to 7 microns or 10 microns across. I will get, on transmission, I will get Gauss-Laguerre 04 in this case, because it has 8 blades here, I'll get 04. And which means that at the focal spot, I will now have a beam with phase singularity carrying all to angular momentum. And so I now illuminate with this light, I illuminate my axisymmetric object. And here we have what's happening. So this is pretty an interesting looking cross, but that's the optical image of a cross, which is rather, it's about 5 microns across the wings of the cross. And this is the optical diffractive element. And we now drive this, oh no, how sad. Okay, so if it would play, what you will see is that I can now put the diffractive element on top of it and get the cross rotating very, very fast.
So how can you put a refractive element on top?
Well, this is sitting, so this is in the liquid. I'm trapping it, okay, and it's trapped and it's not rotating, okay, because it's axisymmetric and it's in a normal Gaussian beam. Now, this is on microscope slide, so I drive the stage on top of it. I put it on top, then the cross is illuminated with Gauss-Laguerre 02, and it starts rotating. And and the film is rather good actually, because when you drive the optical diffractive element away from it, you can see that the cross stops. Okay? So in normal Gaussian beam, it wouldn't rotate, but if you have Gauss-Laguerre beam of light, you transfer all to angular momentum and you achieve rotation. I'll try to dig it out during the pause and we can look at it. So what is it all good for? Well, you can speculate that you can use it in microfluidic devices for sorters of some sort. So you have red blood cells and you want to sort them, so you can direct the flow the way you want to direct it by having it going through the optical diffractive element through the thing which will make it rotate, and then you sort the whatever cells or whatever it happens to be into compartments where you want to have them. Okay. Now, we can also achieve alignment of elongated objects in non-circular beams. So this is elongated object. and I put it into an elliptically shaped beam, and there will be a force acting on it, and it will align itself with the beam. So we can also play tricks like that in order to rotate things around. So this is, it is due to field energy minimization, not due to polarization, and orbital angular momentum is involved in that. So we can now make experiments like that and see how much orbital and spin angular momentum we transfer to objects like that. And so we here are varying the semi-minor axis, and we're looking at torque efficiency here. And we can calculate it, and we can see how much of total momentum we have. And so what is interesting here is that the orbital angular momentum is quite substantial, and spin momentum is rather small, and we can measure it all. Okay, and this is how it looks like when you rotate a particle, elongated particle in an elongated beam. So the interesting thing here is obviously that the incident orbital angular momentum is 0, but the outgoing orbital angular momentum is non-zero, and you can calculate it as I showed you. So, but the question that we want to ask, I'm not quite sure where I started. 10 minutes. Okay. So, so we can ask how we can measure orbital angular momentum of light. And we already know that we can create quite a lot of orbital angular momentum, so it would be good for driving all sorts of micromachines. So one way of doing it is, let me put it like this, one way of doing it is to decompose Lagrange-Gaussian modes into its components, and then analyze the components. And if you analyze all the components of Gauss-Lagrange beams of light, then you can estimate how much orbital angular momentum you carry. So this is what we'll do. Okay? So Gauss-Lagrange beams of light are self-Fourier transforms. Okay, so the idea goes something like this. If I take incoming beam which has orbital angular momentum, so I'm taking Gauss-Lagrange 0,2, so 2 bar per photon of orbital angular momentum. I put it through a phase hologram, which also is done in such a way that if it were to be illuminated with Gaussian beam, I will produce on the transmission Gauss-Lagrange 0,2. So if I use hologram like that, what I will get in the transmitted light, if I now illuminate it with a beam which does have orbital angular momentum of the same order as the mask, then in first order, I will get Gauss-Lagrange 0, 0, 0. So I'll get normal Gaussian beam here. The transmitted straight through 0 order will be 0, 2. But upwards, minus 1 or whatever you want to call it, interference pattern, will be 0, 4. So I start with 0, 2, in transmission 0, 2, 0, 4, and 0. Okay? And obviously, if I have a 0, 4 here, I'll get 0, 4, 3 here, 0, 6 there, and 0, 2 there.
Good question. There's something about the hologram mask that would tell you that has angular momentum too?
Yes.
In the symmetry?
Yes. So in actual fact, this shouldn't be here. This is actually 0.3. Sorry about that. But depending how it forks, it's a little bit like a dislocation pattern. And depending how many fork bits you have here, it tells you exactly. You can do it in such a way that you know exactly whether it's 0, 1, 2, 3, 4, etc. Okay. So the irradiance at the center gives strength of 0,2 component. Okay, so if I measure irradiance in the center, I can get some more information. And those techniques have been used by a number of groups in quantum information and quantum computation processes, like in Xylem Institute, and my colleague at the University of Queensland has used it as well. So now, assume that you have elliptical beam. Elliptical beam, if I model the composition of an incoming elliptical beam, it will be equal to 0,2 Gaussian beam and 0 minus 0,2. Okay? Two reasonable approximations. There are higher orders, of course, to the sides, but we can forget about it for a moment. What we have is mirror symmetric scatterer, which is coupled with delta L plus minus 2. And we have unbalanced amplitudes of those beams. Okay, so how can we check that this thing actually works in practice? So this was the theory of it. So we can have microscopic experiments. So this is done without the microscope. So we have a laser, I have a little slit, I have an elongated rotatable glass plate, which has structure like that. So this is just a rod, which we have written into a glass plate. Here's my glass face hologram, and some lens and rotating screen, wire rotating screen, just because we want to look what's happening with the transmitted light. And if you rotate it, you have on speckle, so you can look at it better, and you have a camera and you look what's happening. So we are talking, all of it is done in paraxial approximation. Okay, so if I have Gaussian beam, if I look at the decomposition of it, this is how it will look like. Then if I take LG02, this is how it will look like. This is what I was showing you with the pictures before. If I have elongated beam, you can see that I have this elongated structure here pointing in that direction and on the other side in the opposite direction. So they sort of, you could analyze it and see that measuring intensity in the middle will give you information of what you are looking at.
Yeah.
If I now have a rod, yeah.
What is it showing? What is this column, the three columns on the right?
Okay,
Exactly?
so this is, I put Gaussian beam onto a hologram.
Okay.
Okay, so there's a hologram here. I put Gaussian beam onto the hologram and I look how it is looking in the transmitted light. So obviously it's Gaussian beam, so in straight line it will be Gaussian to the side 0,2 because my mask is 0,2. Then I put 0,2 on it, so then I fill in the middle, and then this is 0,4. And then I put elongated beam, and the same thing happens. There is some sort of structure with the direction in it. And then I put into elongated particle, so the elongated particle, you can see that it changes the images of what we are seeing. So if we can measure the intensity in each one of them, we should be able to analyze how much orthogonal momentum in those structures we have. And then we can change the direction of the elongated particle, and you can see that the direction here in the transmitted beam is changing. So it all looks pretty good. Okay, so if I now put the rod into elliptical beam, you can see that if I look at the torque efficiency as an angle of rod to elliptical beam, so I change the angle between the elliptical beam and the rod, you can see that the theory and experiment agree very well. Okay, and if I look at the torque efficiency as I'm changing the face thickness of the rod, so I'm going quite high up, you can also see that the agreement is pretty good. This is all done in my macroscopic environment. And the efficiency, torque efficiency, in this case, why do we bother? Because the torque efficiency is pretty large here. The maximum torque efficiency is very large. So if we want to have a lot of torque transfer, that's the way to do it. Okay, so what we have seen is that I have significant transfer of orbital angular momentum. It's measurable using holograms. Similar techniques were used in quantum information processing, and spin significant for smaller objects, but not for large ones. And however, it faces quite significant technical problems, and I was hoping to show you latest result with solving those problems, but they are not totally solved. Namely, if we do the same under the microscope, so that's where I want to use it, it's much more difficult to actually do the analysis of the orbital angular momentum. And it is due to the fact that all of the stuff that I was showing you up to now works because we can do the decomposition and still stay within paraxial approximation. If you have highly focused laser beams, which are then going through high numerical objective lens, it's a mess. And paraxial approximation is really not yielding under those circumstances. And so, what can be done? That's the question. So now, I have another 5 minutes before we take a break? Okay. So, I can have alternative torque mechanisms. It doesn't mean that I don't want to know orbital angular momentum transfer in the geometry I was having before. We're still working on it. And in principle, you can build a setup where you do the pattern recognition using SLMs, and that's what we are working on at the moment. But I don't have fantastic results about that. Okay, so alternative torque measurements mechanisms can be a simple alignment mechanism. So if I have electric field, we all know that I have induced dipole moment, and the dipole will align itself with the field. So the question is whether elongated particle will behave in the same way. And here is elongated particle. And don't tell me that that doesn't play. No, okay. So this shard of glass, when illuminated with laser light, believe me, it turns around in the laser beam. Okay, so this is alternative method. And again, if I want to look at the torque efficiency with this glass rod, which has certain dimensions, again, I can change the angle, and we can see that it's looking pretty good. And it's compared to T-matrix model, and it compares very well. So this is torque efficiency of this elongated shard in plane polarized light, and again, there is some sort of maximum size of this rod which will give me maximum of torque efficiency. But you can see that the torque efficiency, comparatively speaking, with orbital angular momentum is it's 5%, while it was 0.8 per photon before. So it's not very good. Okay, so I think I'll take the break.